In this video, we're going to look at using the LM358 op amp as a follower. And this op amp works really well with single supply, and so that's what I'm running on right now. Just a 5 volts at the rail at the moment. And this is it for the circuitry. That's literally it when it comes to the op amp. Of course, you have to get something to input a voltage, and you'll probably want a load that takes advantage of that circuit, the voltage I mean. But in any case, we have the output there. There is just a direct connection to the inverting input. And if we zoom in right here, we do have to power the op amp, so I didn't show that on the schematic. You don't always see that. If there's one voltage that's being used throughout the circuit, that voltage will be across the op amp. So there is the positive voltage and the negative voltage, which is ground here. So there's a little jumper right here, very small, a little piece of metal right there. It's not insulated. So we have that. That is to the output, the top pin, the inverting input, the non-inverting input, and to kind of reduce clutter and everything, I just have a jumper going from the output over to there. We can put a load over there whenever we want. So in any case, that is the basic operation. So right now I'm monitoring the voltage of this voltage divider right here. That's the cable here goes to alligator clips. I clipped them to jumpers and put the black one on the negative rail, the red one to the middle pin of this trimpot right here. And you'll see I can change the voltage down to 0 volts or up to 5 volts. And there's a resistive element going across there. I pretty much assume you know all this already when it comes to the trimpot as a voltage divider. So there is the voltage. Now here I have an LED and a resistor that the cathode, you can see the resistor goes to the negative rail, so the cathode, the short lead, is connected to the resistor. Long lead, the anode, is up here. Usually you'll see a resistor before an LED, but order doesn't matter as long as the polarity is correct. We're going to power this directly from the trimpot right there, and you're going to see a voltage drop at the oscilloscope right there. It's actually dropped to about what the voltage of the LED is. If I go to the resistor, you'll see it drop even more, quite significantly. And so there's practically no current actually flowing right now. The power supply does not even detect any current flowing at the moment. So we only have a voltage buildup because of the voltage drop of the LED. So what we're going to do is, we already have this wired as a follower. So the voltage that we put in, it will output that same voltage, it will follow it. And so what we're going to do is pluck the 100 ohm resistor, bring it over here, and the output may be high or low right now because we're in a floating state. There we go, the LED went on. So the output is high right now just because it's a floating state. We're not giving it a signal. And so now we'll give it a signal, and you'll notice here that the voltage held steady at the oscilloscope right there when we plugged that in. And so we can take the voltage we're measuring, we'll pluck this out, and kind of got wedged in there. Now we'll put it to the output right there, and you can see we went back to exactly the same voltage right there. So the voltage that we're feeding here, we can change it. Let's go up to that's 3 volts. It probably won't output 4. We already know that's a limitation of this op amp. We'll probably have to just go to 3 and settle on 3. And there you can see we got 3 volts spot on. We can try to raise this. There we go. So that's just the limit of the output. So if we want a higher voltage, we can just take the power supply right there. It's set to 5 volts right now, 4 milliamps of current. And we can go, we don't want to hit 20 milliamps of current. There we go. We can go 10 volts and we're still limited below 20 milliamps of current. And we come here, you can see the voltage went up there. The LED is quite a bit brighter now, and we don't want to go up in voltage. That would be more current. So we could use a higher value resistor though. So let's actually do that. Since we're dealing with 10 volts, that resistor might have started getting hot after a while, but there we go. 410 ohm resistor. You can see the voltage held the same, but the current went down right there. So we have 1, 2, 3, 4, 5 volts. The trim pot is set halfway, 5 volts. So it's that easy. The voltage you set to the non-inverting input will be what the voltage of the output is if you tie the output directly to the inverting input. Because remember, it's comparing the two voltages. And ultimately, when you have the proper feedback, which we do right now, it holds the voltages the same. So even with different loads, it will hold the voltage the same. So now, it's really nice that we can set the voltage with the trim pot as we want just by turning it a little bit. But the light dependent resistor is a more interesting circuit. So first off, we have the potential of dealing with 10 volts, and so a 220 ohm resistor to protect the LED is not going to cut it. So there we go. Now we can go up to potentially 10 volts, although the output stays a little shy of it. So there's only 8 squares right there. We can change the divisions to 0.5 volts. Actually, I want to go to 2 volts per square. There we go. So we got 2, 4, and about 5. Now I'll turn this all the way up. You can see 2, 4, 6, 8, and a little bit more right there. So in any case, we're going to yank this anyways. Might as well leave that there. And we're going to set the light dependent resistor so that when it is brighter out, the LED will be on, and when it is darker, the LED will be off. And so we're going to put that to the positive rail and then to the non-inverting input, pin number 3 down there. And we need, for a voltage divider, that's a variable resistor, we need a fixed resistor on the negative side. And we'll have a voltage out right there. So I'm just grabbing a 10 kilo ohm resistor. Exact value doesn't matter, it will change the sensitivity a bit. But if you get it dark enough, then the light dependent resistor, if it's dark enough, will have millions of ohms of resistance. I think we may have reached that. I'm not sure. And if we get it bright enough, then the light dependent resistor has virtually 0 ohms of resistance. So we'll see the LED get brighter right there. And we can see the voltage. Remember, it's 2 volts per division right now. Went up a little bit. I'm surprised it's that high actually. There we go. If we cover it, it goes way down. So let's make this look a little more natural. So we're about 7.5 volts right now. It went up a little bit, and now it went down quite a bit. And so we get it darker, of course the LED goes out. Now, if we want the opposite, we want the LED to go out when it is bright and then on when it is dark. So that's the opposite situation. All we have to do is switch the light dependent resistor and the fixed resistor. Put the fixed to the positive rail right there, and the light dependent resistor to the negative rail right there. So it's darker, the LED is on, and we'll zoom back, look at the voltage too. So it's darker, the LED is on, and now it's brighter, the LED is pretty dim now, but it is not off. So we'll look at that. There we go. Now it is off, and we get it dark enough. It is on pretty bright. We can look at the voltage. It is up, I think, about as high. It's going to go. So we can actually probably get it up a little bit higher. There you go. We're off the chart there. But in any case, yeah, light dependent resistor, a little more interesting than the trim pot, but it's a bit harder to set it exactly to what you want. So now when I put together this diagram, I was going to use a couple fixed resistors. I forgot to change them to 100 kilo ohm right there, because this was for the transistor version. We could use 100 kilo ohm resistors there as a voltage divider. I did that in earlier videos because you don't need any current the input just looks at the voltage, although a tiny bit of current does leak through. So, but not really enough to influence anything, especially for circuits like this. Now, we're going to move on to the Zener diode. So the Zener diode, you put reverse bias, so it's wired in the way that is harder to conduct. But it has a Zener voltage, where it does start conducting. And so, we will remove the light-dependent resistor, and I'm going to grab a random Zener. So right now we have a 10 kilo ohm resistor right there, and I'm not sure the exact value. It's either 5.1, 5.6, or 3.3 volts, and I'm going to put that in there, reverse bias, and of course we can look at the voltage of the output to see what it is. So we got 1, 2, 3, 4, and a little less than 5. And so if we give it a little bit more current, that was the 10 kilo ohm resistor. Let's go right to a 1 kilo ohm resistor because I have that handy right now. I'm not sure the exact voltage we're going to get. I think probably about 5.1. So we got now 1, 2, 3, 4, 5, and a little bit more at the output there. So that's the Zener voltage. Now, one nice thing about the Zener voltage is that it's the Zener voltage of the diode. And the lighting is not looking too good right there. But we have the 10 volts right now. You can see the voltage there. If I drop that one, I'll go down to 0 basically. But you can see I lower the voltage, and until we get too low, it holds steady. So there you go. So by 7 volts, it's holding at 5.1 volts steady. So that's the nice thing about the Zener diode, is you can change the power supply voltage and your load will have a steady voltage held to it. And so that is the 5.1, and I'm surprised I needed a 1 kilo ohm to keep it from dropping that much. But in any case, here's another one. Again, it's reverse bias, the direction that's harder to start conducting. And this is the 3.3 volt. Really clear right there, Zener diode. Again, that will hold steady as the power changes, as long as it's not too close to 3.3 volts. And so now this will be 5.6 volts. Pretty certain on that. And we got 1, 2, 3, 4, 5, and a little more than half, about halfway right there. So that's the 5.6 volt Zener. So that's another way you can use this here. So these op amps, they don't output unlimited power. Usually they're limited to a current. We can probably short circuit this, and all the ones I've seen so far on the data sheet, it says it has unlimited or some other term where you can actually short circuit it, so it will prevent too much current from coming out of it. I don't know if they all do that though, so make sure you look at the data sheet and test it out ahead of time under careful conditions. But in any case, these are pretty indestructible. I did destroy a few, but I was testing, one out, and I wanted to test something. Maybe it was the output short circuit, I can't remember. And I would pull one out of the board and replace another, and it had a different pin layout. So even if it's a single op amp, a lot of times it has a different pin layout, and the power pin goes, I think the ground pin is generally down there, but the power pin I think goes there sometimes. And I think I fried them that way. So whenever you swap it out, make sure you check the pin layout. And I think I did check the pin layout even and forgot to move the jumper. So you do have to be careful with powering them. But other than that, I don't think I destroyed any from any other goof up other than applying power to the wrong pin. So in any case, hope you enjoy the video. Thanks for watching. I'll see you in the next video.